So, good afternoon. My name is Pilar Barreiro, and I am going to talk this afternoon about, in a general framework, nuclear imaging of food products, and a little bit later I will stick into the details of the talk. First of all, I would like to thank the organizers for letting me give this talk, especially in a video format, because I was unable to attend the meeting. And also, I want you to tell you that if you are seeing this record just now, it means that we failed to make the transmission in the proper date. So that's why you might be seeing some of the slices in Spanish mixed with some of the slices in English, because this is not the latest version for the transmission. So, as I said, good afternoon. The first image I'm showing you is in the left, our research group, which is called Tagralia Physical Properties Laboratory, and on the right is the team of the European project Inside Food. And in green we have the title of the conference, and also a slight bit of humor, taking into account that it should be around after lunchtime. So after this slide idea, let me try to tell you something about the project that we're dealing with. Is Inside Food. These are ideas that have been taken out of the pure website. So you might access the website directly by looking at Inside Food European Union, and you will see that Inside Food aims at measuring food microstructure with an idea of having the spatial distribution of food components with different type of tomographic and spectrographic techniques. So in my case, I'm using mostly magnetic resonance imaging, and when I say I mean all the team of Tagralia, and also people from other institutions like the IFR, the Institute of Food Research in the United Kingdom, who is dealing much more with NMR. But I have to say that our work is so close together that for many years we have been publishing all together. Inside Food is also about the nutritional quality of foods, and therefore it has been working with different type of enterprises, food enterprises like Nestle, for example. In such a case, we have been working a lot on the study of the radiation of cereals, and I don't know whether I'll be able to show up some of these the ideas, but I warn you that you can find in the web some papers of us. I also have here a link into one of our videos. It seems that the link is not working any longer, so I will skip it just now. One idea which is important for us in the Inside Food project is that the research and technology development, and in such a sense we have been working with stakeholders. We have been making symposiums. One of them, Inside Food Symposium, is one of. It has been held in April in Belgium, in the Catholic University, and it's also, you see that there will be and has been technology trade fair in 2013. In fact, these two Inside Food Symposium and the technology trade were held together, and the person in charge in the project was Peter Verbogen. The innovation newsletter is to be published in the near future, and so I again warn you to go into our Inside Food website to look for more details about this particular project. However, you will see that the website looks like what you see here in the picture. You will be able to access different type of newsletters and also some videos regarding the study either of the structure of an apple or either of the structure of phones, which in our case we have been studied with MRI or NMR. So, for the topic of this talk, it will be dealing with multidimensional, multi-slice and multi-scale MRI for quality evaluation in horticultural products. I am giving to you some idea, some look about this supernova star, because in fact what we are dealing with when we are working with MRI is that we are dealing with electromagnetic radiations, and if you think in a wide sense, even the thermal radiation from the Big Bang is available today. So we could see that this technology is not only available today, but it's been there since the universe set up. So it's only our ability to take profit about it for, in this case, horticultural products. First of all, I would apologize for me being the person in charge of this talk, because the person that should be in charge of this talk, it would be Brian Hills. He has been a pioneer in NMR for 30 years, more than 30 years now, and of course I'm just here for a few years in comparison to him. So I apologize for that, and I give all my best regards to him, because I learned a lot with him for nearly 20 years now, so I'm very, very much thankful to him. So I want to share with you this poem about Walt Whitman, the learned astronomer, because he would be happy about thinking of the stars just today, because he was a physicist and he was specialized in astronomy. So let us think of what we know about the structure of fruits. Let me show you here. What you see here is an image that's been taken from the Inside Food webpage. This is the vascular tissue of an apple with a very high resolution 3D tomography technique that has been taken by the Catholic University of Leuven. Again, I warn you that you can go into the web, into our web of Inside Food, and you could have a whole journey into the fruits, because we would be able to see what are the scales within not only food but fruits or whatever materials, from the macro scale to the micro scale to the nano scale. So that's what we are going to deal with here today, and in this case it will be dealing with NMR, nuclear magnetic resonance, and MRI, that means magnetic resonance imaging. So I once showed this image in some years ago. It's dealing with one very famous film about this very famous French comedian, and it's dealing on how we can reconstruct the foods. It was set in the 1970s, and at that stage it was thought as something like histrionic, totally ridiculous for the time being, but it looks like it's no longer so strange anymore. So we are able not only to understand but to reconstruct the food, even with 3D printers. We have seen that there are people that are specialized in that. For example, the TNO in the Netherlands are very much specialized in so. So in my case, I will talk about magnetic resonance imaging as being multi-scale and multi-component. That means that we are not only being able to detect, for example, water, but also different type of components like solutes, or also different type of bounding of the water within the tissue. And we can do it in a macroscopic way by using and dealing with magnetic resonance imaging. That means that we will generate a gradient of the main magnetic field as to encode the spatial information within the product that has to be analyzed. And on the other hand, we have a different instrument. If in the left hand side we have a 200 megahertz instrument, in the right hand side we have a 500 megahertz instrument, which deals with very small, little, tiny samples. And in this case, it's also having the device for magic angle spinning. That means that we are able to have high resolution spectra on solid samples. So in the left, we will be able to convey whole apples and make the tomographies with dynamic behavior at a rate, even at a rate of nearly 1 fruit per second. That is a little bit high. Let's say 1 fruit in 2 seconds. And in the right-hand side, we would be able to analyze the composition. Then, these are the focus. Either we are going to deal with magnetic resonance spectroscopy in such a sense that we are trying to detect different types of components. Either we are going to deal with magnetic resonance relaxometry, and in this case we will try to see how the nuclei come back to the relaxed or the stable situation. And then we have another type of focus, which is magnetic resonance imaging, in which case we have a spatial resolution of the sample. So let me just remind you: spectroscopy, relaxometry, or imaging, and we can deal with all together at the same time. I have selected now a work that is not done by us. This is a work done in 2011. It doesn't look like it's legible, but if you look for it, it is a very large review paper about NMR, and it is interesting because it's not dealing with food, it's dealing with environment. And it is dealing with environment at very different scales. For example, it deals with solutions, diffusion, it deals with solids, it deals with kinetics, and it deals with imaging. And all this has been applied for environment, for example, to address how the soil, what is the quality of soil, what is the movement of substances, and so on. So I think that it is very important that you understand that anything that is being to be explained today for foods or fruits can be transferred to other domains, and in the same sense we import knowledge from other domains into our particular domain, which is food. I also want to, in this same work from 2011, I'm showing you 2-dimension NMR spectra, where you can see that it is being analyzed the organic matter of soil. Organic matter of soil is terribly complex, and it is very interesting to use this type of technology because then you can see different type of materials that can be identified by means of this kind of technology. In this case, as I said, we are dealing with 2-dimension NMR spectra. Let me show you, for example, a 1-dimension spectra, and let me show you the difference of dealing with low resolution and high resolution NMR spectrum. Look, in red you see a low resolution spectra of a solid sample in a 200 megahertz instrument, which, well, in this case is a 500 megahertz instrument without the magic angle spinning. And let me show you in blue the resolution that we get by using the magic angle spinning instrument, which is able to cancel all the inhomogeneities of the magnetic field within the solid sample by making it rotate at a magic angle at a very high speed, something like 2500 turns per minute. So again, I deal with this very, very interesting paper in 2011, where you can not only have 1-dimension profile, but 2 different type of 2-dimension spectra, so that you can address different type of molecules. If this can be done in something so difficult and so strange as and complex as the soil and its organic matter, we can think of easily using it for something much more easier, which is a fruit or an artificial food. I also want to draw your attention to the fact that NMR is also used for cultural heritage analysis. You can see that in many cases these very fancy technologies have been used to analyze the cultural heritage of humanity, maybe coming from 1,000 years ago. So this is really a transversal technology that can be used in many, many domains. The idea, anyway, is as follows. We will have a solid sample. Why solid? Because it's a food. And we will have a main magnetic field, which is called V0. And we may also try to set up a magnetic gradients as to make some kind of spatial encoding. Then, when we have our nuclei, because it is nuclear magnetic resonance, it means that the nuclei of our sample is going to be aligned with the magnetic field strength. Then we will apply a radio frequency pulse, so that the nuclei that are at a certain point oriented with regard to the main magnetic field, they rotate a certain angle. And because all the nuclei are precessing at a certain frequency, which is related to the strength of the main magnetic field strength, what it will happen is that the nuclei will turn and then will go back slowly to recover its initial state. So we will have a magnetic moment in time that will be a complex signal with the following components. This took Brian several days to explain to me, and sometimes I think I don't understand it, but it is rather interesting that to understand that we have a very complex signal in time that depends upon the T2 of the sample. It also, you see that there are 1, 2, 3, 4, 5 components. Some of them deal with how water is bounded to the material and has no complex number upon it. So this means that it's really a relaxation. Or sometimes you have, like in this case, an exponential with the EI, which means that is the imaginary number, with omega 0, which is dealing with the speed of precession, which deals with the magnetic field strength, but also deals with the chemical composition that makes some shift in ppms about the main value. Since this is multiplied by I, this means that this can be analyzed by Fourier theorem, and then we can make a fast Fourier transform, while in this other case it is a relaxation, so we have to use a Laplace transform. In this case, we can see that in this third component we have the spatial gradient. So in this case, by making a spatial gradient, we can make encoding, and this is the way we make MRI. In this other case, we have diffusion, and we have the artifacts of the voids in the samples regarding the main magnetic field. This is kind of a susceptibility gradient, and this is will also allow us to analyze the structure of the samples. Since there is no imaginary number here, then we know that this deals with a Laplace transform. And in the last case, this is interesting, because in this last case we have a V, which is the speed of any material fluid that is flowing through the sample. And this is very much used for geology when you try to address water in the soil, or when you try to address any kind of fluid that is moving in the sample. So what you can see here is that the magnetic moment of our nuclei to go back into their status is dealing with lots of different signals, and if we know the proper order to make the different Laplace and Fourier transform, then we are there. We can extract the information. So, for example, if you want to address how water is being lost, then you need to know how water is going from one cell to another in the fruit. So you might be interested not only in the cells, which are big samples, they are at a level of microstructure, but you might be interested also in the vacuoles, in the intercellular spaces, and so on. You also might be interested in knowing what are the biochemistry processes dealing with the symplast, that means the inner part of the cell, the apoplast, and the ambient. And you can do that by studying the different parts in nuclear magnetic resonance and MRI. But what it is very important to understand is that you have to deal with what is called a representative volume element that has to be addressed. And you can see that there are different references here. I'm sure that in the case of Professor Aguilera, he has dealt a lot about this. And here is a photograph made by Merrick Parker in the IFR just before she retired. And there, here you can see the intercellular spaces, the cells, and even the starch nodules. So it is important to understand if this has been done with confocal microscopy, how would we deal with it in MRI? Okay, so let me show you. This is Melado 2010. Melado is Angela. Angela is making the PhD. It's at the latest stages just now. And what you can see here is how an apple looks like when there is water going inside. Here we have different type of videos, 3D videos of apples that are made with 3D high-resolution NMR. And there we can see that we have all the vascular elements, and we can distinguish very well different structures. And we also can see that the contrast of the images changes a lot due to the type of parameters in the sequence. Not just the sequence, but also the parameters in the sequence. And also you can think that you can use MRI as to drive the sampling system. So while you cannot see any type of defect from a sample, by making the non-destructive tomography, you may decide where to sample and then make high-resolution spectra as to address what is physiologically happening in the samples. So we are talking about multiscale, we are talking about MRI, we are talking also about time resolution, and we are talking about relaxometry, 1D relaxometry, 2D relaxometry, and we are dealing with taking relaxometry for different parts of the volume, so we can make a Laplace inverse transform, so we can detect different type of structures and different water mobility at subpixel level. A pixel level, a voxel here might be of micrometers, and here we can have a subpixel resolution of nanometers dimensions. So what you see here is that by making 2D spectrorelaxometry, we can detect different areas in a sample and detect how the water is moving from these parts. And of course, we can then make some quantitative analysis on this particular matter. The important thing is that once you have analyzed all this, then you get a very nice picture of what is happening in your apple, and then you can try to modelize all this by making a 3D version of your food, making the nice 3D reconstruction of using the proper kind of lattice, and of course you make the multiscale picture of your fruits. For example, here in B we have a microscopic view, then we have a mesoscopic and a microscopic nearly at the level, and even at the level of nano structures. Here you see the cell walls, the cells, some type of middle lamella that is in between the cells. So you can see that we can modelize differently and have different values of this tissue that have been analyzed either by MRI or NMR. So then we can decide whether we are going to deal with temporal modeling or spatiotemporal modeling. And it is very important because then we can make this modeling and understand how physical, what is called the apparent properties deal with. So we have the apple, we have the tissue, and by knowing the properties of the tissue that have been analyzed with different tomographic techniques, then we can modelize for example, the movement of gases, and then we have a whole picture of the apple and deal with some problems, for example, in this case, voids that appear in the apple due to the anoxia in the inner part. So this is a work done in 2011 by Peter Verboven and the group of Bar Nicolai that deals with not only experimental values, but what is called in silico modeling. And in silico modelings have many interesting properties, because it allows you to evaluate the what is called the effective properties of the tissue and transit from a microscopic to a mesoscopic and to a macroscopic view. So these are examples of gas diffusion, and it is very important to understand that sometimes it is not so easy to understand why things happen. For example, this is an apple, this is a pear. Apple floats and the pear sinks. That means, of course, this is more dense than the apple. This means that, for example, apple has more voids inside. Okay, so let's us imagine or deal with the point that they have the same amount of sugar and the same amount of water, so the tissue is equally dense. It is due to the presence of void that the apple behaves as with a lower density than water. So this is important for gas diffusion, and many small properties that arise from the analysis of 2D NMR spectra and MRI allow us to understand things that it would be impossible in any other case. So the idea or the conclusion would be that the knowledge of the theoretical knowledge at current stage that can be addressed through experimental technologies that are very complex, like MRI or NMR, allow us to make a lot of multiphysics modeling, and these multiphysics modelings will allow us to address emerging properties from the living tissue and the living materials. So the idea is that by making some kind of fusion between experimental analysis and modeling, we get a very deep even view of things. So just to end up my talk, I would say that I will use the words of the famous poet Yeats about the choice. This is an image in 2011 when I was working in the summertime with Brian. I spent there a summer. I learned a lot, and I think it was he was already rather I don't know how to say, but he was suffering a lot, but we did enjoy very much all this summertime. So I wanted again to go back to his memory and to apologize for the lack of knowledge that I had. Brian had a very deep faith, so I'm sure that somehow she will make it to be somehow looking, and he will be a little bit cross with me about playing around Brian's life. But since it's Brian, I think I might be forgiven for having this idea. So just to finish, always look the right side of life, and try to read broadly and think widely. I want to thank our institute and the service for this opportunity of giving the talk. It's called GATE, Gabinete de Asistencia a la Tele-Educación. And I would like also to tell you that we have a literature blog where you can join in Spanish or any of the languages that you would like to talk with. Thank you very much, and see you next time.